Hello everyone. Good morning, good afternoon, good evening. Assalamu alaikum wa rahmatullah. It depends on from where you are joining the program. Welcome to Big Bang Data Science Solutions, Data Science for Good program. This is a Ramadan program, free program as you know, in exchange for a small donation to any non-profit organization. Thank you so much for being part of the program, and welcome to week number 4, session number 2. We are still actually in the process of understanding the data, so we learned about the 5 number summary. Today we are going to learn about the correlation analysis. And so let's take a look into the data one more time. So we are going to load the data one more time, and let's take a look at what we have. So in this data set that we have, it's 41,000, 41,188 records and 21 columns. The question that probably could would come to your mind is, do we really need all these 21 features? Actually, there are 20. We have 20 features, and we have one target variable. So in total it's 21. So the question is, do we really need all the 20 features? What if we have 41,188 records, and we got here, let's say 300 columns? Do we really need them? As a rule of thumb, the more data that you have, the better your learning would be, and also the less columns that you have in your data, the better your analysis would be. So we have to find a better way to handle the high dimensional data. So there are a lot of ways to do it, a lot of ways to handle this high dimensional data. So let's take a look how to reduce data dimensionality. How do we know which features to include or exclude? How do we know which features that we are going to use for analysis and which features that we cannot use for the analysis? And these are all the features that we have. So which feature out of this list should we really need to make a determination on the target variable? Is there a way to do it, or simply we can exclude or include a variable because we like it or we don't like it? So this is our target variable, and all these features, they are the output, the input. Which one do we need to remove? Which one to keep? We cannot definitely build a model using all these features. And today I'm gonna teach you some scientific methods that we could use to simply reduce the dimensionality for your data and keep only the features that they are strong predictor, they are strong influencer, they are strong columns or strong features that would help to determine the output of the target variable. So in theory, there are two ways to reduce the dimensionality, either using the feature selections method or feature extraction method. either using feature extraction or feature selections. Okay, feature selections, and this one is features extraction. Then slash engineering creation. Okay, there are two ways to reduce this dimensionality. Okay, so under feature selections or selection, we could do a machine learning. We could do feature selections with machine learning, and we could do it without machine learning. So we could do it with machine learning, and we could do it without machine learning. Okay. So here we go. So we can do it either, as I said, for both feature selection. We could do it uh, with machine learning or without machine learning. Feature extraction, we could do it with machine learning, and we could do it without machine learning. Okay, so without for feature selections, we start with without machine learning. There are a lot of methods that we could use. The first one is simply your prior knowledge. Okay. Second, we could do no, some correlation analysis, and we'll explain all of these concepts. That is, without machine learning. Feature extraction without machine learning. We're talking about aggregation. Number two, flagging, applying flags. Number three, mapping. Number four, yes, aggregation, flagging, ratio. Number five, others. With feature extraction selection with machine learning, we are talking about feature importance. Number two, we're talking about backward backward selection, forward, backward selection, forward selection, stepwise selection, and number three, there are others. There are a lot. For feature extraction using machine learning, with machine learning, we are talking about, let's say, principal component analysis. If your data is linear, if your data is non-linear, we are going to apply a kernel. It's called kernelized principal component analysis. Number three, another supervised learning is called linear discriminant analysis. Number four, QDA, quadratic discriminant analysis, and number five, others. Okay, and for this one is going to be another number three, others. So when you have, as I said, as a rule of thumb, we need to learn better, to learn better for any business problem that you want to tackle using analytics. To learn better, we need more data. More data means more columns. Sorry, more. We need records or rows. And we need less data columns. That is, that is the rule of thumb. If you want to learn better for any, if you want to learn a behavior, a phenomena using analytics, we are going to need more data. So if you have if you have 6 million records, it's better than having 1 million. If you have a million, it's better than having 100,000. And but we need more data, but with less columns. So if you have 500 columns, it's worse than having 150. If you have 150, it's worse than having 50. But the question is, how do we eliminate some of the features? How do we know which feature to leave and which feature to remove? So that is called, in general, it's called dimensionality reduction. And as far as I know, there are two methods to reduce the dimensionality of your data by simply using feature selections. Feature selection is nothing but finding which feature to include or which feature to exclude. Simply means out of these 20 features, which one we can leave and which one we can remove. It's selecting out of all the features that we have, specific features using, of course, some scientific method. And for feature selections, there are two methods. Either we could use machine learning to help us select features to keep and features not to keep, or we could use we start with non-machine learning or without machine learning to determine which features to keep and which features not to keep. Okay, so we are going to start today with feature selections without machine learning. And of course, another method to reduce the dimensionality of your data by simply extracting, creating new features out of the existing features. So you could have, for example, You could have data that looks like this, and you have here this is January sales, February, January, February, March, January, February, March, April, May, all the way to December. So we got here 12. We got 12 columns. So we could transform all these 12 columns to one column. That is so this is months. We could transfer. We could aggregate this into a year. So we reduced the dimensionality from 12 to 1. That is called feature extraction. This year it's not in our data, but we were able to create this year out of the 12 months. So that is called feature extraction or feature engineering or feature creation. In feature extraction, we create new features that we don't have in the data by doing some aggregations, flagging, mapping, applying a ratio, or others. If we were to use machine learning for both, for feature selections, we could use a feature importance, and which we are going to learn this later in the program. We could use backward selections, forward selections, stepwise selections for regression analysis, and of course there are a lot of things. I'm simply naming a few to help you at least start with. If we were to use feature extractions using machine learning, we could apply principal component analysis. If our data is linearly separable. If your data is not linearly separable, we are going to apply a kernel to that. It's called kernelized principal component analysis. So PCA is unsupervised learning, where it does not include the target variable in its mathematical computation. For LDA, QDA, they are supervised learning, where the target variable is part of the mathematical calculations. So that is some of the methods of how to reduce your dimensionality of your data without losing some critical information, without excluding a feature that is critical. Today we are going to talk about prior knowledge, feature selections without machine learning, and we'll talk about the prior knowledge. Prior knowledge is simply your knowledge of the features. Basically, in most of the project that you will be working on, just stay away from any to personal information. Like for example, can anyone give me an example of too personal information?
Social security?
Yes, social security number is not going to add any value. If either you have it or you don't have it, it is not going to add any value whatsoever, unless of course the social security is what you're trying to analyze. What else?
Credit card information.
Say again.
Credit card information.
Like what?
Credit card, right? Any credit card
Yes, credit card number.
number, yeah.
Yes, and names of the person. Amir, Mo. I really don't care who you are. Just give me. I don't care. Who you are. To make a determination if a client will be. You will be yes or no. So names. I don't think names is gonna make any difference. Email addresses.
Phone numbers.
Phone numbers. numbers, physical, street address, addresses. Yeah, think about it. Anything that is too personal information, just take it out. You really don't need to include this type of information in I mean, that type of the columns in your data. It is not going to add any value whatsoever, unless, of course, if you're trying to analyze names, then you are going to keep the names. If you are trying to analyze social security numbers, then you need all the social security numbers. If you are trying to analyze email addresses, but that is a rare incident. Okay, that's too much, too personal information. Just take it out. Not without any ceremony. You can take it out. That is called prior knowledge. You could also take anything that is IDs. Number two, anything that is IDs. Can anyone give me an example?
Bank account number.
IDs. Client ID. Transaction ID. Yes, account number.
Is driver's license considered an ID?
Yeah, drive license. Yeah, I think drive license. It has an ID. Account number. Driver license. Driver license ID. Yes. Anything that is an ID. I mean, sometimes you are going to see, why these IDs that are not, they could be removed because simply they are random numbers. They don't have any value. They don't represent any value. Simply a number that was given randomly to a person. So, student ID, patient ID. When you go to hospital, they create an account for you. And of course, you are going to have unique ID. Okay. And number three, the way you could remove without any notice is what we call the constant what you call constant columns. Like if you have one column with one column with the same value. Okay, I'll give you an example. So you have a small data set, and in your data set you have a column called age, and everybody is 11. You got 6 million record, and everybody has an age of 11. So it's constant. So simply remove it. No need to use that. No need. Okay, so probably we could add that here. We could add it under. Constant values. Okay, any question, concern about this? Any questions, concerns, doubt about the process?
So would you do this at the ABT level more or after?
No, ABT is over now. Now we are in the data. We have the data now.
Okay, so
Now we have the data. We were able to read the data, So you are going to do it at the data level, not at the sorry, ABT level. ABT is simply a conceptual need of data, what you are going to need as far as the data is concerned. And when you get the data, of course, you might they will give you, when you say, okay, give me demographics, I need to specify them. No, you could even specify them. You say, hey, I need age, and You look into your age. Out of your 6 million records, all of them they have the same age. All of them they are 25. Everybody is 25 years old. So just remove it. It's a constant value. It's a constant and a constant value column. Just remove it. Okay. Khan, is it clear?
Yeah, it's clear.
Okay. Other questions, concerns before we proceed, please. Okay. Now we are going to talk about the second. Yeah, that is this is the prior knowledge. This is a prior knowledge. Prior knowledge. Okay. Too many information. Take it out. Any IDs. Take it out. Any constant columns. Take it out. Sometimes, yeah, you are going to need IDs, especially if you are working on fraud detection or transaction detection, any detection problem, you might need to find out the source of the problem. So you might need to keep these IDs. You might need to keep some of the IDs. It depends on what you're trying to analyze. Okay, now we are going to talk about the correlation analysis. Yeah, correlation analysis is you know the correlation analysis is statistics. Statistical analysis is a part of statistical analysis. Is simply we are trying to analyze the mathematical relationship between variables. So correlation analysis always going to be between 1 and -1. Okay. So correlation analysis always going to be between -1 and 1. And of course, in the middle, we are going to have a 0. Okay, when we are talking about data, now we have columns. And yeah, we have a lot of columns in there. And of course, we have a target variable. Where is the target variable? There we go. And we have our target variable. Okay. So yeah, this is our target variable. It's also called a label. It's also called an outcome, a response, dependent variable, and the others they have different names. They are called. It's also called a Y variable. Now the others they are called. They have many names. Inputs, X's, features, independent variables. They are also called this. predictors, etc. So we are gonna use X and Y. So we are gonna use X and Y. That's what we are gonna use now. So using the correlation analysis, we want to find the mathematical relationship between X and Y. So we are looking for X and Y correlation. And also we are going to look for X and X means age and the job, age and the marital is going to be X, and different X's. And of course there is another one, it's going to be X to itself. Okay, so we are going to start with X and Y. So for the correlation between X and Y, if it's a zero, if it's a zero means there is no influence between X and Y. There is no mathematical influence between X and Y. So if age, for example, the correlation between age and the term deposit is equal or closer to zero, we are going to eliminate age because mathematically there is no influence between age and the term deposit. So we have to take it out of the list. If it's above zero, going all the way closer to one, it's a positive correlation. If it's all closer to one, it's called strong positive correlation. Means if let's say X and Y, the correlation between X and Y, it's closer to one. It's above zero. Means if age goes up, the term deposit will go up. That is, that is positive. When the relationship is above zero, means they are going one direction. If the correlation between age and term deposit is below zero, it's a negative correlation. Means if age goes up, the target variable goes down. They are going two different directions. If the relationship between X and Y is equal to zero, means they are neutral. No relationship. So can anyone give me a scenario where we might have X and Y going in the same direction? A scenario. Anyone, please?
Exposure to someone with coronavirus and getting COVID.
Yeah, you're talking about the distance.
The distance? Oh, yes.
Yeah. Let's that's too complicated. Let's just simply think about something that is very, very, very obvious. Let's say that we have you are analyzing house prices. So you got you got a small data set like this. Okay, and we have here house price. We got here age. We got here number of rooms. Okay, and of course we got some values in there. Okay, so age, I believe age and house price should be negative. Why is that? If 80, you have a house for 80 80 years old, of course the price is going to be very low. So age is up, the price will go down. And we have a house that is only 5 months. 5 months is very, compared to 80 is a very small number. The price is going to go up. So age and the house price, if the more age houses that we have, the less price you are going to get. So that is going two different directions. Number of rooms. If you have a house with 10, of course the price is going to go up. If you have a house with 1 room, of course the price is going to go down. So this is going the same direction. So this is a very good example of the relationship between X and Y. They could go the same direction, means they have an influence, they have a mathematical influence between them. So we are going to keep this X here, and if or they could go different directions, but there is an influence in there, we are going to keep them. But if they are neutral, if they are zero, we are going to remove the X. So that is the relationship between X and Y. Any concern, any doubt, any question on the correlation analysis of X and Y?
Question, brother.
Sure.
Now, when we are looking at it, so we are looking at each feature,
Yes.
each one of them.
Each one of them.
Yeah, instead of the whole thing.
Yes, we are looking for X, X1 and Y, X2 and Y, X3 and Y, X4 and Y, X200 and Y.
Okay. Now, for the first line that you wrote here, where you're writing X and Y, X is has all those components inside it, isn't it?
So X simply X is all these features here.
I see. Okay, one by one.
Yes, one by one. This is
okay.
And
Thank
the Y does not change. The Y is the same.
Yeah. Okay. Yep.
Okay.
Thank you.
So it's X here represent every single column of whatever n columns that you have in your data. So we are going to go with X1 and Y, X2 and Y, X3 and Y, X4 and Y, Xn and Y. And we are going to look for numbers. If the number of X1 and Y is 0, remove X1. The number of X2 and Y is greater than 0, keep it. And below the 0, keep it. Above 0, keep it. Equal to 0, remove. That is X and Y.
Oh, thank you.
Okay.
Yep.
And now let's talk about the X and X. X and X is the opposite of X and Y. X and X is the opposite of X and Y. We are going to keep, for the X and for X and Y, we are going to simply remove anything that is closer to 0. Okay, and for X and Y, X and X means age and job, age and marital, age and education, age and default. We are going to keep only anything that is closer to 0. Keep. If you have anything closer to 1 or around somewhere in here, that is highly correlated. They have if for example age and duration, the correlation between age and duration is 0.90. They are highly correlated, and this value simply means indicate that both of them, age and duration, they have the same information. So if you leave them, the model will be biased towards them because they have the same information, and it's considered a duplicate information. So of course we don't want to fool our model by keeping features that carries the same underlying information. So we have to keep only one of them. Which one? That's something that we are going to determine later. But one of them will go home, and one of them will be kept for the modeling. So anything above 0 or below 0, when it comes to X and X, should be further investigated to determine if they don't, to determine if we should keep them or remove them. X and itself, it's always going to be a 1, always going to be equal to 1. No, so we don't worry about this. So the 2 things that we need to carefully determine is the relationship between X and Y. It has to be greater than 0 or less than 0. And the relationship between X and X, it has to be closer to 0. And the correlation always going to be between -1 and 1. And correlation, by the way, is simply, mathematically speaking, correlation is a standardized version of covariance. Correlation is between -1 and 1, and covariance is between -infinity and infinity. So I think the correlation is covariance of X, comma Y divided by standard deviation of X times standard deviation of Y. So you could use covariance, but with covariance, the range is very high. While in correlation, the range is between -1 and 1. Okay, any question, concern about this? Yeah, please don't be shy. And if you don't want to speak out your question, simply put it in the chat or send it to me in private. I will be more than happy to read it for you guys.
Why do we need X and X if we're trying to find a correlation between? I mean, isn't the whole point to find out something about the target variable?
Yes, but sometimes some of the features might have the same information. So why do we need to look into X and X? To simply fight the multicollinearity. Now, if you have in your data set height of a player and the shoe size, I think both of them will indicate if a player is tall or short. So you are having information twice. Just skip one. One is enough. So that is called multicollinearity. Is a concept in data science, and it's a problem. If you have a high multicollinearity in your data, it will create some bias. Okay, clear?
Yes, thank you.
Yeah, welcome.
Excuse me. Is there any like a automated process to do this kind of correlation?
Yes.
In statistics? Because this seems to be a very rigorous process. If you have 300 or 3,000 columns, that's a lot of data.
You have talking about if your question is if there is any method or function to calculate the correlation, yes, it is. Yes, we have it. So now let's jump into Python now. So we were able to read our data from previous session. So anyway, we started with the data dictionary. We have a lot of variables in there, and we have a target variable. So we were able to read our data. Number one, we imported the packages needed. Let me clear out the output one more time. So we are going to import the packages. Then we read your data using the read CSV method of the pandas. Then we removed, we cleared and cleaned the naming, column names, applied the tail, the head function. Then we renamed the target variable. And of course, we looked into the shape, we looked into the info, we looked into the describe methods to help us understand our values. We looked into non-numerical values. We renamed the target variable. We renamed the values of target variable from yes to no to 0 and 1. We applied some histograms on features we already found out that we have a lot of problems in our data that we need to handle later. And so then we did also the bar plot for bar density plot and bar plot for categorical data. And now we are going to do correlation analysis. There we go. Very simple things. And now we are going to do the reason why we need to look into the correlation between x and x is multicollinearity. So now let's take a look. We are going to do, and by the way, the correlation analysis, there are a few rules. For the correlation to work, we are going to need a few conditions. Yeah, for correlation. Correlation analysis. Number one, it has to be pairs. Pairs means if you are trying to find the correlation between age and the target variable, if we have 41,188 target variables, we have to have 41,188 records for age. It has to be pairs. Number two, it has to be real numbers. That means if you look into the data, for example, if you look into the data here, we have some categorical, and later we are going to transform this categorical into numeric, into zeros and ones. So those zeros and ones, they are not real. They were transformation of categorical data. Real values, like for example, an age is a real. It comes in. We did not transform it. We did not transform. Age. Age is a real. Duration is a real. We did not transform it. If we were to transform marital status into numeric, we are going to have we'll create three new columns. They would have a value of 0 and 1, but those 0 and 1s, they are numeric, but they are not real values. So correlation analysis is still going to work, but you are not going to get an accurate analysis, an accurate relationship, because the values are not real. Number three, the relationship between your data has to be linear. It has to have some type of linearity, either positive linearity and negative linearity. If it's scattered, there is no way you can calculate. You still can calculate the correlation, but the value might not be accurate. And there is another fourth one. The fourth one, dependence in the pen. Yeah, I think I spelled it. I cannot read. These are the four conditions for a correlation to work. Going back to our data. So now we are gonna run the correlation analysis, which only works I run the correlation analysis. Now this is what I did. Number one, we created an object, and we simply stored all non-object, all non-numeric values. And out of non-numeric values, we have 11 out of 21, 11. So 11 features out of the 20, 9 of them, they are non-numeric. So, and the correlation only works for numeric values. So now we run the correlation, and all I care about now is x and y. Let's start with x and y. So this is x and y. So we got the age, and of course we got the correlation always going to be between -1 and 1. So the correlation between age and the target variable is 0.03. It's somewhere in here. The correlation between duration and term deposit is 0.04. Something here. This is very good one. This is very high. This one is very good. This one is good. And of course, term deposit and term deposit is going to be a 1. Okay, so and the campaign and the target variable is somewhere, it's a negative, it's minus something here. Then previous, it's, so this is 0. It's something, 0 point is something here, something, it's almost half. Minus 29, it's negative, negative, positive, negative, negative. But out of them, 0.3, 35, 13, 29, 23, 32, 40. So out of these features, if we were to remove few, which one you think should be removed?
The ones that are negative, the one first, the conference index, it's like 0.05. It's a very small correlation.
Yes, that one is true. Yes.
Anything that's close to 0.
Yes.
Like 0,
Yeah.
0.
In general, anything, but just be careful. For now, we are gonna apply this rule. Anything that closer to 0 should really be removed. Okay. So that is the two. Yeah, 0.4 is going to stay. I think 0.06 probably should be removed. But again, this is simply trying to explain to you guys the process of elimination using the correlation. But be careful. Be careful. Even though it's a minimum, it could be it could be a good influence. But for now, we are going to remove anything that is closer to 0. Anything that is closer to 0. So age is going to go home. Campaign is going to go home, unfortunately. And the conf ID index is going to go home. So we started with 21 features. Of these 21, 9 of them, there are 3. One of them is a target variable. We got 9 of them. They are categorical, and 11 of them, they are numeric. Out of these 11, 3 of them, they are going to go home because they don't have any correlation between X, to the target variable. And now let's take a look into the correlation between X and X. Correlation between X and X. Let's see if there is any strong correlation. There we go. Okay, as you see, age and we are going to see always a diagonal. Yeah, this is a correlation between a variable and itself. Always going to be a diagonal out there. Age is going to be always a 1. So let's take a look. All of them. So this is 12. Minimum. All of them, they are minimum. We got 13 there. We got 14 there. We got 37 there. 29. 27. 58. Minus 58. Yeah, this is minus 58. 58 again. 42. 50. Yeah, this is this 90. Yes, here we go. We got 97. Here we go. We got two here. Okay, 97 and 90. This is very, very high, and that is correlation amp var rate, and these two. Okay, what do we have here? 19, 50, 27. We got another one here. And 97. Okay, 90. Good. So now we know that we have something, a few variables that very, very close to 1. We got -1, 0, and 1. So we got here, let's say, amp var rate, and it's highly correlated with Euribor and number of employment. So, and we got here Euribor var 3M. It's highly correlated with amp var rate. And yes, so we got three variables. They are highly correlated. Yeah, and of course, so the question to you, out of this, what do you think we should do with these variables?
Get rid of all of them except for one.
Yes, which one?
I think you should check the correlation to the target variable. Whichever one is the most correlated, keep that one.
Yes, that is true. Thank you so much. Yes. So, of course, these three, they should go home. Now let's take a look. Amp var rate. Amp var rate is minus 29. Okay, and we got here Euribor. Euribor, where is it? It's 30%, and the last one is number of employed, NR, number of employed, is 35. So we are going to remove, as you see here, 35 is higher. So we are going to remove now amp var rate, and there we go. So we are going to remove 1, 2, 3, 4, 5. So we are going to remove 5. Okay, and what we have to do here, then we are going to create a list. No, 2, delete is going to be simply, so we know which one to remove, and we are going to remove age campaign, and we are going to remove also amp var rate. So we are going to remove age and campaign, and amp var rate. Okay, and yeah, Euribor, and so it's going to be 1, 2, 3, 4, 5. Yes, that is what. Now this is the list we are going to remove. And if you are not good in going through the values, the numbers, we could build we could apply the the heat map. Okay, let's try this. Apply the heat map. So again, the correlation is between -1 and 1, and we got the same color in the diagonal. It represents the variable and the correlation between a variable and itself. Age, and age is going to be white. And we look for strange numbers, strange colors. So this is one, another one. All these strange colors probably should be represent how strong they are, how strong the relation is. The more you are closer to white, the less the stronger the correlation is. So this one, they are no, the one is a one. So the white color is a one. This is a one. So the correlation between amper rate and airborne is closer to one. The correlation between airborne and amper rate is one. And number of employment is one. And there's another one here. So this is called heat map. And now, so we have a list that we will delete later, but now we know a list of items that we can remove using some scientific method. So in this today's session, we learned two methods to eliminate the features. We learned to use how the prior knowledge. In prior knowledge, we could use anything that with too personal information, or anything that is in IDs, or anything that is constant. And in correlation, we learn to use correlation between X and Y and X and X. So any concern, any doubt, any question?
Brother Mo, one question.
Yes, sir.
When we did the X and X to find the correlation, I understood that part, but when you remove the variable, you compare the value with the
Amir,
Y.
your audio is not clear. Can you please speak up a little bit louder?
Yeah, so is it better now?
Yes, it's better.
Okay. So when we did the correlation between X and X, I understood that part, but when you removed the variables with a high correlation, you compare the value with the Y variable.
No, so yeah, for XX, we find out there are three features. They are highly correlated. Three features, they have the same underlying information. Which one we are going to keep? Of course, two of them, no, we are going to keep out of the three, we are going to keep only one. Out of the three, we are going to keep only one. Which one to keep? We are going to keep the one that has a strong, very, very strong correlation with the Y.
I see. Okay, that's the part that I didn't understand. That's just the methodology. Is that correct?
Yes. No, it's I think it's a rule, not a methodology. Probably it's a rule. So yeah, we find out we find out for the one that highly correlated is number of employed, highly correlated with amp rate, var rate, and another one which is Oriborn 3M. So one of them should be kept. Which one to keep? We are going to keep the one with the strong correlation with the y. And we out of these three, the correlation between the first one, m var, and the target variable is minus 0.29. The second one is minus 3. The third one is minus 34. Which one is strong correlation with the target variable?
And our employed.
Yes, we are going to keep this one. Others, bye-bye. And I believe, we are going to keep this one. Sorry, we are going to keep this one. So let's take a look now how many features we are going to remove. So we are going to remove, this is 1, this is 2, 3, 4, 5, and we are going to keep 1. So we got age. Yeah, we got age, we got campaign, we got par rate, and conf index. So we are going to remove this also. Yeah, someone asked in the chat, isn't the light color close? Yes. And it depends. It depends on the scale. Yeah, depends on the scale. So yes, the dark is closer to -1, and the light is closer to 1. And when we are looking into the correlation between x and x, we want to find something that is in the middle, something that is not dark, is not white. And when we are looking for correlation between x and y, we are going to keep anything that is closer to 1. Yeah, so we are going to keep anything that is closer to the light color. Okay, folks, so that's it for today. I'm going to dismiss you guys. I promise to dismiss you because most of you guys have been. Next week, there is no classes. So please use the time to go through the recording and reach out to me if you have any concern, any doubt, any question. I'll be more than happy to do a one-to-one session to clear out your doubt before we proceed with our we proceed with other sessions. So one more time, any question, any concern, any doubt? Going once, going twice. Thank you for the business. I'll talk to you the following week. Until then, you guys have a great rest of the day, great weekend. Assalamu alaikum.
Thank you very much.
Thank you.
Thank you.
Yeah.
Thank you so much, Brother Mahmood.
You're welcome.